Hey, and welcome to Need It Make It. I'm Mike. Parts like these, they can't be 3D printed. They need to be stiff, they need to be durable, and they need to have extremely tight tolerances. Well, we're going to test that theory out today to see if even these small parts can be printed, and then we're going to see if they can actually work. So, stick around. Each day we're getting closer to that 100,000 subscriber goal by 2025, and I would like to become one of the biggest 3D printing channels on YouTube, and I need your help to get there. So if you haven't subscribed already, consider subscribing. So I'm in the process of restoring this old lathe. This is a South Bend Model 9A lathe, and the majority of the lathe works just fine, no issues. But over here at the cross slide and at the compound, especially the cross slide, there is a ton of wear in the lead screw and also in the nut. And I've already taken it apart so we can take a closer look at it, because I'd like to see if I can use 3D printing to make a stopgap solution for this problem so that I can get this lathe back up and running, and also to set the clearances correctly so that if I want to get a new piece CNC machined, I can go ahead and do that and have confidence that it's going to work out. So here is the original cross slide nut, and this is the original lead screw for the cross slide as well. And you can see where there was very little use, very little wear in here, and then far, far more. These have come to a sharp point. And the same goes for the inside of the nut. Everything comes to a sharp point, and there should be about 1 millimeter of a flat spot, but there's none whatsoever. Now I have a replacement lead screw, so I don't need to worry about that part, but I don't have a solution for the nut. This is the new lead screw. This is far better, but unfortunately it's still not good enough. This needs to be replaced completely. So what I've done is designed a brand new model in Fusion 360, and I've tried to match this Acme thread profile, and I've tried to match the diameters as well, both the inner and the outer diameters. And I was really close with this model. Unfortunately, it does not quite fit. It's just a little bit too tight, but it's really close. So I've made some adjustments to this model, and I'll reprint this in PETG. But I also want to try a completely different material to see if I can use a 3D printed model as a temporary solution on my lathe. Now this is the original compound screw and the nut as well, and you can see it's quite a bit different, quite a bit smaller, but there's very little backlash in there. The lead screw looks really good. So I don't think there was a lot of wear. I don't think there was a lot of use on the compound. But while I'm at it, I would still like to create a new one of these that fits just a little bit better and try and get rid of as much backlash as I can. This is the now 4th attempt, and the clearances here that I've allowed are basically non-existent. So I've been struggling a little bit to try and get the fit just perfect, but I also decided to do a cutaway version because I wanted to see how accurate this thread really was and whether I needed to make any adjustments to the model as well. Oh, still too tight, yeah. So let's see what's going on with the cutaway version. Maybe there's something else that I did wrong or did not account for. Yeah. Well, there's your problem. It looks to me like there's something going on with the thread pitch. So the thread pitch that I need is 10 TPI. This is 12. So I think what I did was I used the stock Acme thread for this diameter of rod, and it's giving me a 12 tooth per inch. So that's why I've been having so much trouble. So unfortunately, this is a custom thread size then. This is 10 teeth per inch. And this one is also 10 teeth per inch, and it is also a custom size. This is 1 inch measurement. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 teeth per inch, perfect. For the nut that's gonna fit on there, I managed to get a pretty good fit. I put a flat spot on this one as well, and that way I could print it laying down. It's just a tiny bit snug, but I think that'll be fine, and these tend to wear in. And then this one, Really nice fit on this one. And then the nut itself. Beautiful, beautiful fit. So I'm pretty confident now with the models, and as long as the filament is calibrated for flow and for pressure advance, I think we're going to have good results. So I think it's time to try this. Ultra ABS glass fiber. So this has 25% glass fiber, but this is not normal glass fiber reinforced ABS, if there is even such a thing. The glass fiber is within the center. So the idea here is that the layer bonding, layer adhesion is supposed to be better on this, but still have the properties of a glass fiber reinforced filament. I don't know why. I was expecting this to be black, but it's green. Oh, cool. There's a little bit of a rough texture to it, and the consistency of the filament, it looks a little bit bumpy. That's probably the best way to describe it, and it feels a little bit bumpy, like an undulating surface. So I wonder whether that'll come into play when we're printing with it. I'm going to go ahead and calibrate this filament on the printer, and then we can try and print these parts that we're actually going to use on the lathe. I just finished loading the filament in, and I have to say this is some of the most stiff filament that I've ever had. It is also pretty brittle though, so it snaps fairly easily. Hopefully that will not cause any problems. This is the fine flow calibration test, and the flow here needs to be increased just by the smallest amount. For this calibration test, it looks pretty good up at about 16 millimeters, so that's 16 times 0.02. That gives us 0.32 for the pressure advance setting for this filament in the slicer. It's time to print these parts, and with these threads being so critical and having severe overhangs, I'm printing this with a 0.08 millimeter layer height. There's going to be no cooling on this, and it is going to be printed inside of a heated chamber at 55 degrees Celsius. So I was pretty sure that this was not going to work out well, just because of when I looked at the texture on the spool and the filament, the way it looked. And I mean, it is a little bit rough, but this fits absolutely perfect. I didn't go too extreme with my calibration. I just did one flow calibration and I did one PA test. That's it. It is absolutely perfect. So here is the setup. This is including the new lead screw, not the old lead screw that was even more worn. And here is the new one. And I'll tell you what, it's just a little bit loose on the fit. There's a little bit of movement, and that is partially because this is threaded and then there's a pin that comes out. This pin goes down and this one comes out at the same time to lock everything into place. I don't have that in place on this one, unfortunately, but I'll see what I can come up with for that. So I'll probably need to reprint this just a little bit larger. So I've gone ahead and remade them. These are completely solid this time, and I've adjusted the flow up just ever so slightly so that I would get a little bit tighter fit. So this one fit really well, and the same goes for this one here. And this one is lockable by this set screw. Compound is good. It's really tight, feels good, nice movement. Unfortunately, the cross slide, that new lead screw that I put in there, there's something wrong with it. It looks like somebody has done a repair and put two shafts together, and when they did, they've not centered them correctly. They're not concentric. And so it rubs. This is how much backlash I have in the cross slide. It's quite a bit better than it used to be. The compound is far less, 1/1000th of an inch backlash. There's a bit of roughness there. That should be far smoother. So I am going to change out the tool just to see if there's an improvement there. That is quite a bit better. I had a really close look at the tool I was using at first, and just the tip of it is broken. So I've replaced it with a brand new one. I'm going to try this on some steel. So I was pretty impressed with that glass fiber filament, and I really wanted to take something that I've been holding on to for quite a while and go ahead and make it. And this is a prototype that I came up with for my lathe, and it's a threading dial, and you need these if you're going to be doing a lot of threading. And this is the previous one, and this is one that I downloaded, and it does not look anything like the original. It's extremely spindly, and I couldn't even get it together. This didn't even fit in here. So I thought I would design one that looks more like the original. And it sits on the lathe right here, and when you want to activate it, you just tilt it forward to engage it. So I had this printed with PLA. I was never really confident that this was going to work out. Also, this is not a solid part. So after having experimented with the glass fiber, I thought, why not? And it's green, but it can easily be painted. I'm not worried about that. I really like the texture, and there are a few other small improvements to this as well. And the only part I didn't print on the QIDI was the dial face, and that's because I want to have the contrasting color. That is the finished thread dial, and you can see that that face looks pretty darn good. And I still have the 3D printed cross slide nut, and I still have, although you can't see it, the 3D printed compound nut in here as well. I'm just going to go ahead and try and do a little threading, very quick threading. I'm doing a scratch pass first, and then with this thread I should be able to pick up any of the increments on the dial face and engage them when they've reached 12 o'clock. And then when you're finished, you can just plunge in way too much and it will auto-eject. Well, I think you get the idea that it works. The problem is me. Well, I have to say I'm impressed that I was able to get this to work at all. And I was able to machine steel with pretty good results. I have brass, and this was a high-speed cutter, and the results look pretty good. And then some aluminum that I cast quite a while ago. High-speed steel cutter, and not too bad at all either. That's great, the glass fiber works, but what's to say that some of the other filaments wouldn't work as well? So I have made up a bunch of samples, and these are all printed 100% solid. I have ABS, I have Creality's Hyper PLA, I have PETG carbon fiber, and I have the QIDI glass fiber 25. Now you might think that your parts are not warping, but a lot of the time what happens is that it pulls up on the build plate. So I have some light coming from behind, and you can see that there's just a little bit of warpage on the completely solid ABS part. This is the PLA, Hyper PLA. This has quite a bit more warpage on it. This is PETG. Somewhere in between ABS and PLA. This is PETG carbon fiber. Still a little bit of warpage, similar to ABS. And here is the glass fiber. I don't actually see a gap at all. Look at this one. I didn't expect that it would be that good. It's not moving at all. Next, I want to test how stiff each material is and how they compare. So this is the little test rig that I've set up. So we'll apply a small load to this end, measure the amount of movement. This is the fulcrum point, and this is held stationary so that this can't rise up. So it has only one choice, and that is to bend down. I have a bit of an approximation of the test that we're going to perform. This end is pinned, so it cannot raise up. Here I have a load cell that will read out over here. So we'll apply 10 pounds. And the actual load at that fulcrum point is far greater. I'm going to go to 10 pounds. 10 pounds again. For functional machine parts, we need something that is as stiff as possible, and the results of this test showed that. For Hyper PLA, we had 11 millimeters of deflection. For PETG, we had 15. For ABS, we had 13. For PETG carbon fiber, we had 11. And for ABS glass fiber 25, we had 10 millimeters. And now we're going to take it one step further to see how much force it takes to either permanently bend these parts or to break them. I'm hiding behind the jig because I'm a little bit afraid of getting hit if any of these decide to break. The Hyper PLA is a lot tougher than I expected for something that's so stiff. The basic PETG is pretty flexible, printed with infill. It likes to break violently, but smaller and printed solid like this, it seems to be far more flexible and more resilient. The PETG carbon fiber is a bit surprising to me because it's stiff, but it's also not breaking. The ABS seems to do what it normally does, whether printed with infill or not. It stretches first and then it breaks. And the ABS glass fiber 25 acts more like cast iron. It really does not enjoy bending, and it breaks with quite a bit less force than the ABS. The glass fiber filament is the stiffest, but it's also very brittle. If it's being used where it needs to be able to flex, it's probably not a great choice. But if it is sized correctly for the job and it can remain stiff without flexing too much, I think it would work just fine. So yes, these small parts can work, and they've been working for me all week, and I've been enjoying using the lathe without so much slop in it. Is it a long-term solution for the lathe? I don't think so, because there are good reasons why we use brass and why we use bronze for those nuts. But as a temporary solution, yes, I think a stiff but brittle filament actually works pretty well here. The design of the threads lend themselves well to applying pressure over a large surface area and across many of the threads, so I think it is possible. If you'd like to see more testing and experimentation on this filament, let me know. And I will have a link below if you think this filament is the right stuff for some of your projects as well. If you happen to need this threading dial, I will put this on my Patreon page and you can download it for a couple of bucks and print it for yourself rather than paying $200 for a new used one. I also designed the gear as a hobbed style gear, which fits the lead screw far better than the original. And with it being plastic, it is not going to wear down that screw like the original steel version would. Thank you to each of my patrons for helping to support this channel and making these videos possible. And if you would like to help support this channel as well, there is a link down there below. Also, thanks to QIDI for sending out this filament for me to test out. Take care, everybody, and we will see you on the next one.